All right. So friends, do you feel comfortable doing a dot plot? Is that something you feel comfortable with? Okay. Now the second part is describing the shape. Which shape best describes this data? So on a dot plot, and I'm just going to make up one. Bless you. So this is relatively normal. Okay. Everything's kind of clustered together, kind of forms, looks like a bell. Okay. And when I say a bell, if I were to draw on a normal curve, it looks something like that. Now, we didn't really talk about normal curves, but I think it's easier to take a look at saying that creates a normal distribution. But what if I had my data look like this? If I tried to do a bell curve here, notice you have a tail way out to the right. So this is what they call skew right. Okay, so the tail out to the right is skew right. Hayden, I realized the homework I had assigned, I had to touch everything, so we're just kind of going over it. All right, so if that's skew right, what would you think this would be? Let's see who's paying attention. What would that look like? Yeah. Let's make that tail longer. Skew left. Okay. Now, when you're skewing things to the right or to the left, that just basically means that the mean is being pulled to the right, the mean is being pulled to the left. You have outliers to the right, or you have outliers to the left. Okay, does that make sense? And then what I can do is I can go back to any of those problems and we can take a second look at them. Then there's something that looks like this. And this actually looks like this. This is called bimodal. It's like bimodal. Okay? That just means that if we were to have a normal curve, we got a couple humps in there. If you had 3 humps, trimodal, 4 humps, call it 4-modal. There's not really. You rarely see anything beyond bimodal, but it theoretically is possible to have more humps like that. But that's basically what the data looks like. Okay? So, with that information, excuse me, that I just stated, are there any problems A through E on number 1 you'd like me to work out? Anything on page 117? Yeah. Letter B? B as in boy? Okay, let's take a look. All right, so number 1B, right? All right, so we have, that's nice, they gave it to us in order. Okay, so we have 1, 2, 3 dots at 2. We have 1, 2, 3. We have 3 on all of them, don't we? Okay, I have to remember, there is a term for that. I got to remember what it means. Oh, duh. That kind of information is just called rectangular. Which which there's really nothing to it. You can't draw a normal curve. Sometimes they would make a curve like this to make it look like a rectangle. Anything else off of problem number 1, A through E, that you'd like to take a look at? Happy? Satisfied? Problem number 3 says, study each situation, decide which shape each data is likely to form. The number of runs scored each game by a baseball team. Okay, so there are some baseball games that are pretty high scoring. There are some baseball games that are pretty low scoring. So what do you think? What do you think some baseball games like? Let me ask you this. I don't know how many baseball players we have in here, but what's the highest score you've probably heard about in baseball? I'm just curious. I mean, have you ever heard a score maybe in the 20s? Is that possible? Okay, the 30s? I don't know. Maybe in the 30s? I mean, has anyone ever heard like a baseball score in the hundreds? Gosh, I hope not. Boy, that would be. That is a great, unbelievable, nonstop people running the bases type of thing. So a lot of baseball games. I mean, I would say you could have baseball games that are wind up as 1-0. You could have some games, so if you had total runs or total points would be 1. You can take it all the way up to whatever. So I'd be curious to think about, like, if we were to think any of the Rockies games, you could have 1 to, I don't know, say 30. And you might have something that looks like that. Well, I understand. And I was just basing this off total points so we can accelerate it up. I mean, I guess if you looked at a whole season, and I realize I don't have enough games there, I was going to draw like 180 things, but that data is kind of all over the place. Agree? So there's really not a shape that we could attribute that to, but I guess it depends upon each season. Should this year's season look like next year's season or the season after? I think each season is pretty much independent. Each game is pretty much independent. Like, if you hit 2 home runs in a game yesterday, that doesn't mean you have to hit 2 home runs today. Doesn't mean you could hit no home runs. Doesn't mean you could hit, many more. I mean, it's kind of hard to sit there and say, okay, yeah, data is data. But I think that would be very easy to look at saying, I couldn't distinguish a shape. I don't think it's skew right or left. I'd say there might be some times where you could have it something like this. Let's say it's just a little league team. So maybe you could have something that looks like this. So this could technically look a little bit like a skew right because of this outlier out here. That was the one where the pitcher of the other team was horrible. They're having to just throw underhand to you because the guy's shoulder's not working, so he's just doing this. And one's getting a big hit. But so I guess that's possible. But again, there's not really a conclusion we could make. So there's all kinds of different things that we could justify. The high temperature each summer day in Denver. Well, this summer might have looked similar to other summers, but not exactly like other summers. I'd say we have high temperatures ranging from the 70s to the low 100s, I would say we would have, if we had the temperatures, and maybe we started with, let's do it like 10 degrees, 20, 30, 40, 50, 60, 70, 80, 90, 100, 110. So if this is based on summer, I don't think we had any 10, 20, 30, 40 degree high temperatures. We might have had like one cold day, had a high in the 50s. I'm just speculating. I'm not saying this is factual. We might have had a day in the 60s, probably some days in the 70s, 80s, 90s, couple in the hundreds. Let's pretend I can draw a normal curve really well. So that could appear kind of skew left, okay? And it's skewed left because these were some strange days. The days where we actually had to have a sweatshirt on during the day. Well, no, let's face it, we're in Colorado. If it's in the 50s, we're in shorts, right? That's one of the things. If you ever travel anywhere in the winter that's, warm, like Phoenix or Florida, you'll see people in winter parkas and you're in shorts and a t-shirt. They're like, aren't you freezing? Yeah.
Doesn't the way that the data is set up, or doesn't like having it start at 10 and go to 100 time, doesn't that change the way it is now?
Absolutely.
So wouldn't it make more sense to start at 50?
50?
I mean, since that's the first time there is a temperature.
That's true. Let me ask you this though. Could we have a summer day that's 10 degrees? Is it remotely possible, especially now with how weather patterns could be changing? Could we have that freakish, hey, we got to freeze, and people are like blowing out their sprinkler lines? And
I mean, I guess.
I mean, maybe. I'd say.
But out of the data that was provided for this, doesn't make more sense.
Yeah. Yeah, I think you might be right. And I think that's a valid argument. Yeah, I like that. I mean, it's a great thought.
Because we can't prove that there wasn't a day.
Yeah, like this part of the region is pretty unlikely.
Yeah.
So I think I like your idea of starting at 15 going up, or maybe even 60 going on up. I mean, we know we're not hitting the 110s in the Denver area. Now you go to the Grand Junction, they've got some warmer days. And sometimes way out on the eastern plains, sometimes they'll have some warmer days than what we actually are. But yeah, I mean, I definitely probably wouldn't count by like ones.
Well, yeah, because then you'd have 110 different dots.
Yeah. So.
And you'd have to count each individual day of summer.
Yep.
Or the high temperature today.
Yeah, and so what I was doing on this is like if it was going from 50 to 59, that would be this guy.
Yeah.
60 to 69 would be this guy. 70 to 79 would be these guys. 80 to 89 these guys. 90 to 99 these guys. 100 to 109 would be those guys.
Which that makes sense. I'm just.
No, I like it.
Like that skews the data.
Yeah, I mean it gets to a point with the data where how far do you really need to start at zero, or because theoretically I could add zero right here. Yeah. Does it make sense during the summer? Probably not. And I think you're absolutely right. So, and it's just I would probably not mark somebody wrong. Now, if we were talking about things in the millions, and we're like in the 600,000, 700,000, 800,000 range, starting at zero, that doesn't make any sense at all. And I like your reasoning as well. I think this portion is wasted paper. Like our graph is not showing it, but that's part of statistics. Like if I wanted to try and scare people and say, look how hot it is, maybe I show this. If I want to say, hey, this is what happened, and you're just trying to represent data, then I like your idea even better than mine. So. Cool. Last digit of social security numbers.
What?
So the last digit of social security number of a large group of people, right?
4 hours social security number.
No, I'm not asking anybody. So the last digit of the social security number. Could the last digit be a 0? Could the last digit be a 9? Could it be anywhere in between? Talking about a large group of people, you probably would get a rectangular look. I mean, my last digit's 3. It's like, oh man, we're gonna steal your identity. We know the last digit of your social security number.
Mine's 5.
Yours 5, okay. Does anyone have a 0 for the last digit? Anyone have a 1?
Let me check.
You carry your social security card in your pocket.
I have it in my notes on my phone.
Notes on the phone?
It's so dangerous. I need it for like everything and then I
Keeping
forget.
your social security card in your wallet is one of the worst ideas. That's like keeping your birth certificate and passport in your wallet.
When I first got my driver's license in 1987, your driver's license number was your social security number.
Wow, that seems like a good idea.
8, okay.
Mine ends with a 1.
Yeah, there you go. So we're kind of, I mean, we're talking about 20 some people that we have all different digits. Go ahead. Yeah. So letter C would definitely be rectangular, okay? Because we could go from 0 to 9 and anything in between. There's no rhyme or reason why somebody would have, why you would have a group of people that would all have 9s or all have 0s or anything in between. So I think it goes all over the place. Okay. Yeah, and then in order for Arizona to protect social security numbers, I thought this was funny. They put your social security number in. There was a certain math equation that it ran through, and then it would give you a new number. And then you had people who were hackers who realized what the equation was, so they just undid whatever your equation was, did the inverse operation of it, and they could get your social security number. It's like, guys.
That seems like a flawed plan right
Yeah.
there.
Wait, so how do they get like babies' social security numbers? Like how do they assign them?
No, that's a good point. If it's on your driver's license
Yeah.
and babies don't usually have
No, they would ask what your social security number is when you went to go get your driver's license back in
No,
87.
but, like what I'm asking is like how do they assign them?
I think now it's pretty random. And I would say the social security numbers probably have to go out another digit now because there's too many people. Or too many people for the social security, not too many people altogether. Some people might think that. I mean, if you drive an I-25, you'll agree there's probably too many people. So, unless you're down in Trinidad, then you're probably fine on I-25. Yeah.
No, it actually changed. So most of us were born in like 2003, 2004, 2005 in that range. And for all of us, we're all born around the same time. It's actually based on like where you were born with the state, some of that other factors.
Yeah.
But not too long after you changed, now it's more randomized. So all of us have really easy guessable ones. Because they're all based on the state you were born in.
Gotcha.
And different like days or months.
And that's what mine started out with 202 when I was born in New Jersey.
So 202 laws.
Yeah. Now you just have to guess all the rest. Okay. We're gonna hack you, Stirrup. It's like, sweet, Stirrup's got extra 31 cents. We're rich.
Yeah.
No.
Claim credit for him coaching a soccer team now that I have his identity.
Yeah. All right. Let's see. Number 4 says, assume the data has a mean of 6 and a median of 4. So, what did I say? You had a mean of 6 and a median of 4. Okay. So the median, this is the center of our data. If the mean is 6, what happened to the data to influence the mean? It went to the right, yeah. So this is, you had things to the right, you had larger numbers to the right than you would to the left. Okay, and I would say being that we're probably dealing with 0 to 10, I don't know if we're dealing with the negative numbers in this situation. That's what's taking place. Number 5 says assume the data has a mean of 60. Mean of 60. Assume the data set has a mean of 60 and a median of 60. So I would say this is a normal distribution. Okay? You don't have anything pulling your mean to the right or to the left. It's just falling right in the center. So this is a nice normal curve with our data if we drew that over top of it. Number 6 says sometimes data sets are hard to describe. Can a data set have characteristics of both bimodal and skewed right distribution? Well, do you think you could have data that looks like this? That's bimodal, and it's also, they asked for skewed right, or just skewed. Skewed right, yeah, this is skewed right. So bimodal and skewed right. So I think you definitely could. Okay? I don't know what that data is right now. I'm not going to just make up arbitrary values to say, hey, we have data, yippee. All right. Next one says we have this data set. All right, so I want to pull up our best friend, our graphing calculator, and as it's thinking about loading, I think it's thinking. There it is. All right. And again, I would just go to the calculator on this kind of stuff. Would somebody do me a favor? Would you read me across the top what we have first? 28. What's next? 38. Y'all can participate anytime now. 63.42. 38.
38, 36.
36, thank you. 28.
Yes. 34.
34.
72.
72.
37.
37.
51.
51.
32.
32.
26.
26.
44.
44.
37.
37.
45.
45.
34.
34.
58.
58.
65.
65.
And 40.
And 40. Okay, so we have our data plugged in. Let's turn our stat plot on, and if it's not on yet, it is on. I think the histogram is going to be fine to look at. I mean, we could look at the data points, but we don't really have a Y value to deal. So I'll do with the histogram. Okay, we're good there. And I'm going to go zoom. And we're going to go down to number 9, zoom stat. So that's basically what the calculator comes out with. If I were to try and draw in a normal curve here, what do you think? Skew right, skew left, normal? Skew right. This is pulling it to the right. If we went and did our one variable stats on that information, I would say just by looking at it, our median is going to be a lower value than our mean. Our median is going to be a different number than our mean. Our mean is going to be a bigger number. Our mean is going to be a bigger number because it's skewed to the right. So because it's skewed right, the mean's being pulled to the right. And again, we could just easily say, okay, well, that's great. We look at a picture, but let's calculate the one variable statistics. So we have a mean of 41.9. Bless you. Bless you. And we have a median of 38. Median 38, mean 41.9. Do you agree? Does that make sense to say that the mean is to the right more than the median because of how our graph looked? I think so. Okay. And then you can just, once you do the zoom stat, there's no reason to go change the window. I mean, if you go into and do second trace, nope, I just want to go trace, I'm sorry. So this box goes from 26 to 35.2 where you have 7 pieces of data. Move this to the right. This goes from 35.2 to 44.4 with 8 pieces of data. Oops. This one is 44.4 and less than 53.6 with 3 pieces of data, so on and so forth. Just run through it. That one has 1. This one probably has 2, 3. So all the information is provided with you. I think once you do a zoom stat, I don't think you need to go change your window. I don't think you have to change how it counts unless it totally asks you to. Okay. Describe this data in terms of center, spread, and outliers. It's the center of it. We said what our mean was. Second, quit. So if we went back to our one variable stats, what did we say the center was? It was 38, and the spread is to the right. Outliers are, I think that the 63 and I forget what was the biggest number? 72. The 63 and 72 are what are pulling it out to the right. What do you anticipate the relation between the mean and median? Well, the median is to the left of the mean. The mean is to the right of the median, something like that. And calculate the standard deviation. Okay, so one variable stats. Oops, stat, calculate, one variable stats. Which standard deviation do I look at? There's 2 of them listed. Which one do you want? The SX or the CX? SX, because it's a sample. Make sense? Okay. And again, friends, the more data that I start plugging in, if I had plugged in, like, say, 200,000 pieces of data, these 2 numbers get closer and closer and closer together. Okay? But we always want to look at the sample. Don't worry, I'm not going to assign you hundreds of thousands of pieces of data to plug into a calculator to see what happens. But that's basically it. Questions for me on this page? Feel comfortable? Okay, I will put that, being that you're here, I will put that in the grade book for you. And would you go to the notes for 1-9, 1-9? Okay, so 1-9 are called box plots. And I think because I will run out of time, so I'm just gonna start this, but I won't give an assignment tonight, then we'll finish it tomorrow. Is that okay? Yeah. Okay. Box plots are also called box and whisker. Okay? They mean the same thing. And the box plot is a way to look at our data. And the nice thing is, before I go too much further, if I go back on my calculator and I go second y equals, and I go to my plots, bless you, our data will do a box and whiskers. Now, there's 2 different ones to look at. You always want this one here. This one is not used too often. They just throw it in. So we're going to use this one. Okay? So if I hit enter, and this was the data that we had from our homework, and then if I have to go back and hit zoom stat, this is going to show us our data. Okay? So how you read this information? You have this lower portion, this middle portion here, it's a small rectangle, looks almost like a square, and then we have this third region. So we have 1, 2, 3, we have 4 regions. Agree? Now, sometimes you will have this, and this will end, and you'd have a dot or two further out. Those are extreme outliers, okay? So the box and whiskers consists of this. 25% of my scores fall within this region here. We don't know what the region is, but I know that 25% of my scores fall there. 25% fall in this rectangle, 25% fall in this square, and 25% fall within this region. So half your data, this line here, half is below, half is above. The middle 50% of your data, your IQR, your interquartile range, is here. It's Q3 minus Q1. Okay? So this is a minimum, this is a maximum, not talking about outliers. This is our median, often called Q2. This is Q1. So that's the middle of your bottom data. This is Q3, the middle of your top data. Okay? So box plots, often called box and whisker plots. For mysterious reasons, boxes and whiskers have very little in common. Contain a lot of useful information. These displays are not well understood by the general public, but among statisticians and others, they are becoming increasingly common. And they give you an example. They talked about what we just said. We said they called lower quartile. Lower quartile, you can write anything as Q1. Median, if you want, you can put Q2, though we don't, I just want you to know that it could be referred to as Q2. Upper quartile is Q3. And they have called the upper extreme to the right and the lower extreme to the left. And we don't have any outliers on our data. So as you can see, a box plot has only a horizontal axis. The ends display the ends of the whiskers. If you like the whisker analogy, show a minimum and maximum values in the data set. The ends of the box show that the values of Q1 lower quartile value and Q3 upper quartile value. The vertical line is the median, okay? Each position breaks it into 4 quartiles, which we said. Each quartile contains 25% of the data, with the understanding that the quirky things that happen with box plots and small data sets, therefore a box part of the box plot contains the middle 50% of the data, which happens to be the interquartile range, which we call IQR. And guys, if I ever give you if it says find the IQR and you're like, I don't remember what that is, ask me. I'm happy to tell you it's in our quartile range, which is Q3 minus Q1. The width of the entire box represents the range. The diagram illustrating this is shown below. So they're just talking about that. The 5 numbers that split the box plot are called the 5-number summary. In order that the 5-number summary features a minimum, Q1, median, Q3, and maximum are shown above. Okay, so let me go back and show you something on here. I'm going to create myself. Oops. And it doesn't have to be this way. Okay, so something that they don't talk about is extreme outliers. These would be some extreme outliers. This would be an extreme outlier to the left. These are extreme outliers to the right. So when we look at this, we have 25% of our data here, 25% in here, 25% in here, and 25% over here. You don't include the extreme outliers as any of those 25%, okay? Often those extreme outliers are ignored because it was just a strange event that might have taken place, okay? Other things to know, this is our minimum, this is our maximum, this is our median, which sometimes is referred to as Q2 in some statistics books. This is Q1. This is Q3. The IQR is the interquartile range, which is Q3 minus Q1. And this interquartile range represents 50% of our middle data. Does that seem okay? All right. So that's as far as, oh, one last thing. Where is our mean, our X bar? We don't know where our mean is. Okay? There's nothing to say that our mean has to fall within Q1 and Q3. Okay? If you had some of these extreme outliers, these can pull the mean very far to the right. So our mean could happen over here. Okay? It's doubtful our mean would ever fall outside of this. I guess the only time it would is, let's say we had like single digits. Let's say we had scores out of 10. But then, let's say the teacher decides, okay, I'm going to give 1,000,000 points extra credit if a kid gets this question right. So you always know there's that one kid, right? So you have a kid who got 1,000,000 points on a 10-point quiz. Well, that 1,000,000 points totally could bring the mean over here. Okay? So the mean isn't represented on the box and whisker graph, but it does exist somewhere in the graph. We just don't know. We know the mean when we find the mean using the one variable statistics on the calculator, but that's all we have. So, any questions on this so far? We will continue these notes tomorrow, okay? Sound good? Everybody happy? If you're going to miss tomorrow, I will have this recorded, so please take it upon yourself to watch it.